An important part of any control system is the link between the controller and the real world. For a digital controller, data enter and exit through a parallel interface or through a serial interface. Both data formats are discussed in this section. The parallel interface transfers 8 bits of data at the same time using 8 separate wires. It is essentially an extension of the data bus into the outside world. The parallel interface is ideal for inputting or outputting data from devices that are either on or off. For example, a single limit switch uses only one input bit, and an on-off signal to a motor requires only one output bit. These one-bit signals are called logic variables, and 8 such signals can be provided from a single 8-bit port. This concept will be expanded on later in this section. I've shown a 16-bit parallel cable here because the colors indicate quite nicely the parallel nature of the signals, but just remember we will normally be dealing with 8-bit cables. In other applications, the controller may use a parallel interface to connect to an analog device, for example, driving a variable speed DC motor. In such a case, the binary output of the controller must first be converted into an analog voltage before it can drive the motor. This operation is performed by a special circuit called a digital to analog converter. The digital to analog converter DAC is a circuit that converts a digital word into an analog voltage. It is not within the scope of this presentation to describe the internal workings of the DAC, but a general understanding of the operating parameters is appropriate. The figure shows a block diagram of a typical 8-bit DAC. The input is an 8-bit digital word. The output is a current that is proportional to the binary input value and must be converted to a voltage with an op-amp. A stable reference voltage, Vref, must be supplied to the DAC. This voltage defines the maximum analog voltage. That is, for a digital input of 11111111, Vout is essentially Vref. If the input is 0, the voltage out, Vout, will be 0 volts DC. For all values in between, the output voltage is a linear percentage of Vref. Specifically, the output voltage for any digital input for the 8-bit DAC is as shown. Vout equals input times Vref divided by 256, where Vout is the DAC output analog voltage, the input is the decimal value of the binary input, and Vref is the reference voltage to the DAC. This example has an 8-bit DAC with a reference voltage of 10 volts. If the binary input is 10011011, what is the analog output? First, convert the binary input to digital, then prorate the reference voltage using our equation determined earlier. Pause this presentation and go through this example to check you have understood the concept. If it helps, imagine the output is like a 255-step staircase, and every step up you gain 0.39 volts. After climbing 155 steps, you have reached 155 times 0.039 volts, or 6.05 volts. An important consideration of digital to analog conversion is resolution. The resolution of a DAC is the worst case error that is introduced when converting between digital and analog. This error occurs because digital words can only represent discrete values. as indicated by the stair-step diagram previously shown. For example, the maximum value of an 8-bit number is 255 decimal, which means there are 255 possible steps of the output voltage. The difference between steps is the value of the least significant bit. Because the smallest increment is 1 step, the resolution for 8-bit data is 1 part in 255, or 0.39%. This resolution is adequate for many applications, but if more is needed, 2 or more 8-bit ports can be used together. 2 ports provide 16 bits of data. The maximum decimal value of 16 bits is 65,535. Being able to divide an analog number into 65535 parts means that each part will be much smaller, so we may more precisely represent that number. The following example is taken from the text. A computer uses a DAC to create a voltage that represents the position of an antenna. The antenna can rotate 180 degrees and must be positioned to within 1 degree. Can an 8-bit port be used? The resolution required is 1 part in 180. Because 8 bits provide a resolution of 1 part in 255, an 8-bit port is certainly adequate. In fact, we have a choice. We could have the least significant bit equal to 1 degree, in which case the input values would range from 0 to 180. Or we could equate 180 with 255, which makes the least significant bit 0.706 degrees. The latter makes maximum use of the 8 bits to give a better resolution. But if the system really doesn't need it, the clear, simple relationship of the least significant bit representing 1 degree is desirable. Digital to analog converters can be supplied as a single integrated chip, like the one shown. This is a datasheet for an 8-bit DAC, specifically the DAC 0808. This device comes as a 16-pin DIP, or dual inline package, and uses an external op-amp, such as an LF351, 2 resistors, and a capacitor to complete the circuit. It requires plus and minus power supply voltages, in this case plus and minus 5 volts. The time to complete a conversion is a fast 150 nanoseconds, and the circuit shown has a reference voltage, a Vref, of 10 volts DC. An analog to digital converter, or ADC, is a circuit that converts an analog voltage to a digital word. A typical ADC consists of a single IC with a few support components. Analog to digital conversion is a more complicated process than for the DAC, and the hardware requires some conversion time, which is typically in the microsecond range. Recall the DAC was in the nanosecond range. The conversion time required depends on the type of ADC, the applied clock frequency, and the number of bits being converted. The input voltage, Vn, can be any voltage between 0 volts and the reference voltage, Vref. When Vin is 0 volts DC, the output is a string of zeros. When the input voltage equals the reference voltage, Vref, the output is a string of ones, or 255 decimal. For input voltages between 0 and the reference voltage, the output increases linearly with Vin. Therefore, we can develop a simple ratio for the ADC. Basically, the output voltage is 255 multiplied by the ratio of the input voltage divided by the reference voltage. To start the conversion process, a start conversion pulse is sent to the ADC. The ADC then samples the analog input and converts it to binary. When completed, the ADC activates the data ready output. The signal can be used to alert the computer to read the binary data. As an example of an analog to digital converter, consider an 8-bit ADC which has a reference voltage of 7 volts DC, an analog input of 2.5 volts DC. What is the binary output of the ADC? The output is an 8-bit word that has a maximum decimal value of 255, when the input voltage Vin is the same as a reference voltage Vref. Therefore, an analog input voltage Vin of 7 volts DC would be converted to 255 decimal. Using this set of data, we can develop a ratio and then use that to find the output for the specific input of 2.5 volts DC. The output is 2.5 volts times 255 divided by 7 volts DC. Crunching the numbers gives an output of 91, which is 01011011 in binary. Analog to digital converters can be supplied as a single chip like the one shown. This is a data sheet for an 8-bit ADC, specifically the ADC 0804. Packaged as a 20-pin dual inline package, this device can operate on a single 5-volt power supply and requires an external resistor and capacitor to complete the ADC circuit. The start conversion pulse is applied to pin 3, WR, and the data ready signal comes from pin 5, the INTR. This particular ADC can be connected to a free running mode where it performs one conversion after the other as fast as it can. Notice also that the pin labeled Vref over 2, pin 9, must be set at half the actual reference voltage. For example, if the requirements call for an analog voltage range of 0 to 5 volts DC, then pin 9 would be set to 2.5 volts. The time to complete a conversion is approximately 100 microseconds, making it almost 700 times slower than the DAC 0808 discussed earlier of 150 nanoseconds. This slide shows a position control system using a microprocessor-based controller with parallel ports. This particular system has one output port and 3 input ports. Each port has its own address. The output port is partitioned. 6 bits are converted in a DAC to provide the analog motor drive signal. The 7th bit specifies motor direction, 1 being clockwise and 0 anti-clockwise, and the 8th bit turns on an audio alarm if some emergency situation is detected. The first input port inputs the set point data. The second inputs the ADC data from the sensor, and the third inputs various 1-bit logical variables. In this case, the system has 3 front panel switches as well as 2 limit switches. The limit switches are used as a backup to detect if the load has gone out of its designated range. Operation of the system proceeds as follows. The controller inputs the data from port 03 to determine if the start or stop button has been pressed. If the start button has been pressed, then the set point is read in from port 01, and the digitized sensor data is read in from port 02. Based on its control strategy, the controller outputs to port 00 a binary word representing the motor control voltage. This digital data is converted to an analog voltage with the DAC. This entire sequence is repeated over and over until the stop button is pushed. We now look at serial interfaces. In a serial interface, the data are sent one bit after the other on a single wire. There are a number of good reasons for doing this. First, the cabling is simpler because only two wires are needed at a minimum, those being data and return. Second, shielding a small group of wires, which is often necessary in an electrically noisy industrial environment, is easier. Third, serial data can make use of existing single-channel data lines, such as the telephone system, which may require using a modem. For these reasons, serial data transfer is usually recommended for distances greater than 10 to 30 feet. Because data always exists in a parallel form inside the computer, it must be converted to serial data before coming out of the serial port. This is accomplished with a special parallel to serial converter IC called a Universal Asynchronous Receiver Transmitter, or UART or UART. On the other end of the line, a receiver must convert the serial data back into parallel data, which is done with another UART. Serial data are classified as being either synchronous or asynchronous. Synchronous data require that the data bytes be sent as a group in a package. It is used in sophisticated communication systems that move a lot of data and will not be further discussed here. It also needs an additional clocking cable. Asynchronous data transfer is the more common but slower type of serial transfer and allows for individual bytes to be sent when needed. This slide shows the standard format for asynchronous serial data. Note that the x-axis is time and not showing the signal progressing through the wire. It may help to think of the signal as moving from right to left. First, a start bit is sent, then the data with the least significant bit first, then a parity error checking bit, and finally the stop bit or bits. Some variation is allowed in this format, but both transmitter and receiver must use the same format. The other important parameter in serial transmission is the number of bits sent per second. Standard bit rates are 300, 1200, 2400, 9600, 14400, 28800, 33600, and 57600 bits per second. Serial data transmission is much slower than parallel transmissions. At 300 bits per second, it takes almost 37 milliseconds to transmit 1 byte of data, compared to less than a microsecond for parallel. This is thousands of times slower. Still, for many applications, particularly process control, the longer data transfer times are not a problem. In order to make the serial interface practical, a set of specifications called the RS-232 standard was established. Officially, the RS-232 standard specifies the serial data interface between data terminal equipment DTE and data communication equipment DCE. A common application of the RS-232 is the interface between a PC or computer and the modem, in which case the computer is the DTE, the data terminal equipment, and the modem is the DCE, the data communication equipment. A modem is a device that converts digital data into audio tones so that it can be transmitted over the telephone lines, as is shown here. The RS-232 interface consists of 7 signals. The serial data is sent on pin 2 and received on pin 3. The other signals, such as request to send and clear to send, are used to confirm that the two units are ready to communicate. The RS-232 standard specifies connector types, signal names, pin numbers, and voltages. In practice, the RS-232 standard can be applied to any serial interface as long as one unit acts as the DTE and the other as the DCE. If two DTE units need to interface with each other, for example, a PC to a PC, a special cable called a null modem or crossover cable is used. RS-232 is commonly used in the control field when two units need to exchange data. For example, to connect a PC to a local control unit for the purposes of downloading a new control program. RS-232 serial data transfer is somewhat more complicated than parallel data transfer, but it offers advantages such as two-wire communications and a universally accepted interface. The hardware to handle serial data is standardized, readily available, and reliable. Probably the most common use of serial data is in networking. More and more, networks are being used to interconnect all the units and devices in the control system. Network cabling differs depending on the type of local area network or LAN, but most use the generalized bus system shown here. Typically, each unit on the net has a unique address number and also address detection circuitry. When one unit wants to talk to another unit, it first broadcasts the address of the unit it wants to talk to, serially of course, on the signal wire, and then sends the data, serially, which consists of some number of bytes. All units on the net will receive the address, but only the intended receiver will activate and then read in the data. The interface between the network cable and the PC is done through a commercially available interface expansion card called a Network Interface Card, or NIC. Other devices on the network, such as control units, would require a special interface circuit, which may be built in or available as an external module. Control system networks are discussed further in Chapter 12. This brings us to the end of our look at parallel and serial interfaces.